Hello, everyone, and welcome along to the AMETEK Solidstate Controls monthly webinar. This is our September webinar, taking place today on the 25th of September. Thank you for joining us. We do appreciate you taking the time out of your day to come and visit this webinar and hopefully learn something. As always, I'd like to start off by asking everybody if you can hear me. That is always a good start, because I don't want to be talking to myself in this room and nobody hear me. Kind of pointless if we did that. So I'll just wait for the chat. If you just type in the chat, it's on the right-hand side of your screen that you can hear me, then that would be appreciated. So while we wait for that, thank you. I appreciate it. Everyone can hear me. So let's do the introductions. First of all, my name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solidstate Controls, based out of the Stafford office, which is on the southwest side of Houston, Texas. I think it's 23 years in the industrial UPS industry now, and I've worked with all of the major UPS charger manufacturers. And I've been with AMETEK Solidstate Controls for, I think this is going on my 7th or 8th year. As always, there will be a lag of around 30 seconds between you hearing my voice and me seeing a question. And that's basically because the platform we use is Webinar Jam. It's got to take the signal that I am broadcasting and it's got to change it to Windows-based, Apple-based, iOS-based, and the Android version as well. Couldn't think of the name there. So to do that, there's a little bit of processing time, and it takes about 15 to 20 seconds. So from when I speak to when you hear me, there's about a 15 to 20 minute lag, second lag. And therefore, if you type in a question when I'm talking, I'm not going to see the question until 15 to 20 seconds after I've been talking on a specific subject. And the whole point of that is what I'm going to do is wait until the very end. If you look in the chat bar on the right-hand side, there's two tabs in the chat bar. One is for chat and one is for Q&A only. If you have a question, put it in the Q&A only tab. And then at the end of the webinar, I will try and answer as many questions as I possibly can. Webinar Jam does have a panic button. So if I see in the comments that we are losing connection, people can't hear me, people can't see the presentation, I can press the panic button and Webinar Jam creates a brand new room, invites everybody into it, and we can carry on as if nothing had happened. A very popular question is, will the webinar be recorded? Webinar Jam does record the webinar. But then if you registered for it, you will get a link after the webinar is complete where you can rewatch the webinar at your content. The problem with that version is it's treated as a webinar. Once you press play, you can't fast forward, rewind, or go to any particular section. So it's not convenient if you want to skip through some items like me doing the introduction here. So what London, our wonderful marketing team, does is she takes that Webinar Jam recording, converts it to an MP4, uploads it to our YouTube channel. And if you look in the chat bar, the link is already there because London is wonderful. And you can find all the videos from previous webinars at that YouTube channel if you just click on that link. And those videos are shareable. You can pause, rewind, do whatever you want with them. And the last question a lot of people ask is, how long will the webinar last? And it will be about 1 hour, depending on how much time I speak, how much questions we have, and many other parameters. In other words, whether I waffle on or not. So that's all the introductions. Once again, thank you for joining us. So today, the outcomes are going to be understand basic inverter design, understand the SCI design of inverter bridges, and there's two main types that we use, discuss the components used, discuss something that's called desaturation, and we're going to explore basic troubleshooting. Now, please bear with me with the troubleshooting. You're not going to become an expert by watching this webinar. It's just some very basic, easy to do troubleshooting in the field. It's not going to go down to software levels or how to connect to the software and look at parameters. It's going to be a very high level basic troubleshooting portion. It's still very I suppose in depth and technical, but you know, it takes us 6 weeks to train one of our field service guys before we let them go out. So 1 hour is not going to turn you into an expert, unfortunately. Okay. So the first question is, what is an inverter? And it's a very important question because you need to know what it is doing. And the basics of an inverter is it converts DC power, either from a charger, a battery, wherever you have a DC power source, and it converts that into an AC signal. Okay, and this is the symbol that is universally used for an inverter. We have DC coming in on the left-hand side. That symbol there is for DC. And then we have AC coming out on the right-hand side. Okay, so DC here and AC here. So that is the top-level view of what an inverter does. It converts DC into AC. And it does that by using semiconductor switches. Okay, and the semiconductor of choice, we're going to get onto it in a minute, that we use as an IGBT, but we'll go through these slides just to give you an idea of how it works. So we have 4 switches in this bridge. So we have S1, S2, S3, and S4. And as you can see, 2 of them are open, S2 and S3 are open, and S1 and S4 are closed in this diagram here. And on the left-hand side, we have a positive to negative power source. This is a DC power source, okay? And then in the middle here, we have a motor, a DC motor. And at this moment in time, if we have S1 and S4 closed, if you follow the power flow this way here, because this switch here is closed, we get positive on this side of the motor, okay? Yes, we still get positive down here, but because this is open, S3 is open, it won't get down to this point here, okay? So that's how we made this side positive. And then if you follow the negative down, once again, S2 is open, so it can't go that way. But S4 is closed. So we do get negative on this side of the motor, okay? So let's say in this configuration, we've got positive on the left-hand side of the motor, negative on the right-hand side of the motor. That is going to cause this imaginary motor to turn clockwise, okay? Clockwise. So using switches, we can put power to this motor and get it to turn clockwise. So when we're creating AC, AC moves in both directions. So what we want to do is to be able to turn this motor around and turn it counterclockwise. So to do that, we open S1 and S4. Remember, at this point, they're just switches. And then we close S2 and S3. And once again, now if you follow the power flow, positive goes to here. It can't go down there because S1 is open. It can go down to S3 and make that side positive. Now we have positive on the right-hand side of the motor. S4 is open, so we can't go down there, okay? So that's how we get positive on the right-hand side of the motor now. And for the negative, we just follow the power flow down. S2 is closed, so we get negative here. S1 is open, so it can't go all the way up. And S4 is open here, so it can't go this way here. So that now, in the previous slide, we had positive on the left-hand side and negative on the right-hand side. Now we have positive on the right-hand side and negative on the left-hand side, and the motor reverses direction. So just by changing the configuration of these switches, we can make power flow go one way, and then we can make power flow go another. And that is what AC is. It's when the current flow changes direction, alternating current. Okay. One important thing to remember when it comes to, and this is called an H bridge because it is shaped pretty much like an H. On an H bridge, if you close S1 and S2 at the same time, that is called shoot through. It's something that you should never ever do. And in truth, on all processor controlled inverters, it should never allow this to happen. But if it does, then that's a direct short across a positive and negative of the DC input, which is usually a battery. And that's going to cause high current to flow and basically damage. If this was an IGBT, it would seriously damage that IGBT and cause failure. So we only want S1 and S4 to be closed, or S2 and S3 to be closed at any one time. So that is the basic. That is how we convert DC, which is usually stored in a battery, into AC. Okay, for this one here, it was for a motor, but in truth, if we replaced that with a transformer and did the exact same thing, and we had a secondary on the output of that transformer, then we would create a square wave AC waveform. Okay. Now, as I mentioned before, and I can't say this enough, sometimes people, they think about transistors and they think of amplification regions. Is it linear? And is it in its saturation zone? You know, it takes a small signal and changes it to a large signal. When we think about transistors in the power industry, when we're converting power from AC to DC or DC to AC, we're talking about semiconductor switches. And the semiconductor switch of choice for inverters is called an IGBT, which is an insulated gate bipolar transistor. And basically all it means, and you can see insulated gate means there is no connection, no physical connection between the gate and the collector and the emitter. Okay, basically it uses a field, because you know an IGBT is a cross between a FET, a field effect transistor, and a bipolar transistor. And it uses a gate signal from a FET, which has no connection between the gate and the collector emitter circuit. It just uses a field to turn the collector and emitter on. So that's where the insulated part comes from. And then the bipolar part is the collector and the emitter is basically made up of exactly what a bipolar transistor has. And the current flow is always indicated by this arrow here, and current will flow from the collector to the emitter if we turn the gate signal on. So when I say think about it as a switch, that is the way to think about this. If we send a signal on the gate, then this becomes a short circuit. Collector and emitter become a closed circuit. Okay, and then if we remove the gate signal, then the collector emitter becomes an open. No current will flow whatsoever. And just to add a little bit of technicality to it, there is this reverse connected diode in normal operation. Remember I said current flows through the IGBT this way. So therefore this has to be positive and that is negative. Well, in normal cases, if you have positive on the cathode of a diode and negative on the anode of a diode, current cannot flow. So it's as if that diode is not there in normal operation. But if we have a situation where there is inductance in the load, what happens is if you turn off an IGBT, there can be a back EMF that is generated because you're interrupting current flowing through an inductive circuit. And when that happens, a back EMF is caused, and you will have positive and negative there. And what this diode allows to do is, rather than damage the IGBT, it allows current to flow through that diode. And we usually have a capacitor bank back here in the inverter bridge, and it allows that inductive kick to flow through that diode and back to the capacitor or the battery, whatever the DC circuit is. Okay. So I'm all for analogies. I usually use water, but it's even simpler with an IGBT. It really is as simple as this. An IGBT is like a spring-loaded switch. If you send a signal to the gate, it's like someone presses the button and causes the switch to make the circuit. The collector now has a direct connection to the emitter and power will flow. Okay, and then if you remove your finger from the switch, in other words, you take away the gate signal, the spring pushes back and current cannot flow from the collector to the emitter. That is as simple as it gets. It is a switch that is controlled by an electronic gate signal. Okay, and this is what they look like. In truth, this is the IGBT that we use more than anything, although we do see these style of IGBTs as well. But it's probably difficult to tell on your screen. There's actually two IGBTs in this package. Here are the gate emitter terminals that we connect our gate signals to, and these are the main power signals that we would connect to create our bridge. Okay. The unfortunate thing about an IGBT is, unlike an SCR, which is very robust and can withstand high current situations for a relatively small to medium portion of time, IGBTs really cannot handle excessive currents. If something goes wrong, if the firing signal goes wrong, or you have shoot through, then a fuse really isn't fast enough to protect an IGBT, and this can happen. So therefore, we do have some circuits in place to try and prevent that from happening. But just remember, IGBTs are very, very sensitive devices to high current situations. Okay, so before we move on to how we use them in our UPSs, I'm just going to take a drink. So this is how we use IGBTs in our Micro-ferro, or any system that has a ferro-resonant transformer in it that has a microprocessor. So we have two types now. We have what's called the Micro-ferro SE or the Micro-ferro DSE. Okay. The only difference between the two is the new DSE has the same mimic screen as our DPP pulse width modulated technology. Okay, but what we're doing is we still have positive and negative on the left hand side. So this is always going to be connected to the battery, because the battery is there just in case power fails, and we can still carry on converting DC into AC. Okay, and now we only have two IGBTs for this design of circuit. Okay, and we have a center tapped transformer. So if you look carefully here, you can see the positive is connected to the center tap of this transformer. Okay, very important to understand. That doesn't move, so that is always going to be positive. And you can see negative is connected to the emitter for both of these IGBTs. So what we're doing is, depending on which IGBT we switch on, depends on which side of the transformer we connect the negative of the battery to. And I'll explain this in just a moment. So first of all, we're going to turn on Q1. So once again, remember, power to the center tap of the transformer, it's always going to be positive there. But now, because we have turned Q1 on, remember, when we turn it on, it just becomes a direct short between the collector and the emitter. So negative gets connected to this side of the transformer. Okay. And I'm not going to go into transformer design too much, but whenever you see a black dot, that means that's where the winding starts. And then obviously this is where the winding ends. So we're making a positive signal compared to the negative signal on this transformer. So in truth, what that is going to do is it's going to give us this bottom half, because look, here's 0 and then we turn Q1 on at this point here, and we go straight up. This graph here shows it as 100 volts. So let's say we've got 100 volts DC coming in. So we now, if you measure on this side, let's say the secondary of the transformer was here, this is what the output is. If we had an oscilloscope and we switched Q1 on and then switched it off, it would give us this square wave here. Okay, so that gives us 1/2 of the square wave. And then what we do is we then turn Q2 on. Remember, this point here is always positive, and then that allows negative to be connected to this side of the transformer through Q2. Okay, now this is positive with respect to the end of the transformer, so that is going to give us our positive side, and the amplitude is going to be 100 volts because we have 100 volts going in here. So peak to peak, we're going to have 100 volts in there, 100 volts in there, so it's a 200 volt peak to peak waveform we've created. And if we switch Q1 on and then Q2 on, and we do that at 60 times a second, we have created a 60 hertz square wave from a DC signal. So we have created AC from DC just by using 2 IGBTs and a transformer. It is very, very simple in respects to how we do it. The challenge is doing it in a way, because remember, this is 60 times a second we are switching these IGBTs, and that is every second of every hour of every day of every year. And you know, the minimum expectation lifespan of our UPS is 20 years. So there's a lot of switching going on, and we need to make sure that that happens correctly every time. So that's where the software and the design comes in. But once again, the theory, the principle behind it is very, very simple. Okay. So that was what it looks like. That's nice on the eyes. It's very easy to see what's going on there. This is actually what it looks like in one of our drawings. Okay. So this is the positive and the negative coming in, and it says that's the battery input. We also have a charger connected. So this is a UPS, not just an inverter. And that has the positive and negative coming in there as well. But if you look, this positive comes in here and goes to the center tap of the transformer. So that is always positive. So that's just like the last page that we just looked at. And if you look at the negative coming in here, that goes to this point here, which is connected to the emitter of both of these sets of IGBTs. Now, it's slightly confusing here because we have 2 IGBTs in parallel, but that's basically how we increase the power of our systems. If we had 1 IGBT, it's probably going to do 5 to 10 kVA. 20 kVA would have 2 IGBTs in parallel, 30, maybe 3. As it goes up, we just put more and more IGBTs in parallel. But once again, I'll just through here, through the fuse, down to this point here, we have positive at the center tap of the transformer. And then if we switch these IGBTs on, negative now goes to this side of the transformer, and you will get the negative going pulse there. And then we switch it round and turn these ones on. Negative goes that way to that side of the transformer, and that would give our positive. And we would do that 60 times a second. And then if you measured across that primary of the transformer, you would measure the square wave, and on the secondary of the ferroresonant transformer, you would see a relatively nice AC waveform because of the capacitor and the inductors inside the transformer, inside the ferroresonant transformer. That smooths out the square wave into a nice sinusoidal AC waveform. Okay, so that's the basics of how a micro-ferro UPS works. Well, what can go wrong? Okay, so the first thing that we're going to look at is, okay, the inverter's not operating. The inverter is not running. And on the Micro-ferro, they make a humming noise when they're on. So you should be able to hear that. And obviously the common alarm should not be on. So if the system is on bypass and the inverter is not operating, there's a few things that you can check. Okay. And the first thing is, do you have greater than 105 volts DC going into these 2 points here? And that's basically directly across the capacitor bank that's connected to the inverter bridge. You must have, for a 60 cell lead acid system, you must have more than 105 volts DC, or the inverter will not start, because we take that DC and it goes into these pins here on the control board. And if we don't have 105 volts, the inverter will not start. So that's the first thing. So we need to check, is the battery okay? If you have less than 105 volts DC, has the battery been discharged? Is there something going on with the battery? Is there an external disconnect between the battery and the UPS system that may have been accidentally left open? That happens quite a lot. Or it could be, is the charger okay? You know, the charger should be taking AC and turning it into DC. So we need to make sure that the output of the charger is DC. And remember, always remember, whenever you have a charger and a battery, the output of the charger is in parallel with the battery. So the only way that you can tell if this charger is working is to open the battery disconnect and make sure we still have 135 volts DC going into the system, because that's what it should be roughly to keep a lead acid battery charged and for the inverter bridge to run. So that's the first thing you need to do. And you wouldn't believe how many times we get called out to a system. They say that the inverter has failed. There's something wrong with the UPS. And it actually ends up being something to do with the battery. Because if you have an open circuit battery cell and you have even a 1 second power outage, then the DC is going to collapse because the battery charger turns off. There is an open cell in the battery, so it cannot sustain power to the inverter, and therefore the inverter will go below 105 volts DC. It will trip the battery breaker, and the inverter will switch off. So that's the first thing to check. Another thing is, okay, if you follow the startup procedure here, and all of our UPS systems have the correct startup procedure on the front of the system on a placard. So you should always follow the startup procedure. So for this system, the first item you should do is close the battery input breaker before you even start the charger. Okay. And you should have a healthy battery here. So we're going to say, okay, we know that the battery voltage is greater than 105 volts DC. We've measured that. We know that if we close the battery breaker, the system should start. Well, on our Micro-ferro systems, we don't have an inverter enable switch on. We don't have a switch on the front of the UPS that turns the inverter on or turns the inverter off. Okay. What we do have is an auxiliary contact that's connected to the input breaker B1 here. Okay, and when you close that breaker, if you follow this box up here, here is the B1 aux. Okay, so our control board is looking for the B1 aux to close, which is basically going to supply power to this board here. And actually on the board, what happens is, I can't remember if it's pin 3 or pin 4. 5 volts is created on the board, and if it's closed, that will make 5 volts go back on the other terminal. And that's what tells our inverter to start. So if there's something wrong with the auxiliary contact in B1, which can happen, it doesn't matter if your DC is good and everything else is good. If this contact does not close, the inverter will never, ever start. Okay? So if you have a little bit of troubleshooting skills and you think that maybe the B1 aux contact is bad, If you have a way to jumper across 3 and 4, you can see if you can get that system to start and basically disable the B1 aux contact. Obviously, you will need a new B1 aux contact, and you need to order that from us, but it's a good way to check why the inverter isn't starting. It could be that B1 aux. Okay. Another reason could be is B1 tripping. Now, B1 is it does have a current rating, so it will trip on overcurrent, but it's very, very rare that we see it trip on overcurrent. The most common thing is what we said before, is the 105 volts DC for a 60 cell system. All UPS manufacturers have a way to protect the batteries from being completely over discharged. And most battery manufacturers say, okay, once you get down for a lead acid battery, once you get down to 1.75 volts per cell, you should disconnect the battery to prevent it going any further below that, which could, in theory, if it was left in that state for a long period of time, could cause sulfation of the plates and basically make the battery unrepairable. It won't be able to supply power if it's left in that state for a long time. So what our system does is it monitors the 135 volts at that pin there, okay? And if that goes below 105 volts DC, then this board here says, okay, I'm going to disconnect the battery, and it sends a signal out on these two terminals here to K4, the coil of K4. And the coil of K4 contacts are here, okay? And they're connected in series with the coil, B1 coil here, which is this breaker here, okay? So if we send a signal, we energize K4, K4 closes, we energize using the battery power, we energize the coil, and the coil shunt trips the input breaker at 105 volts. So if the inverter is not operating and B1 is tripping, we need to make sure that K4 is working correctly. And there's two ways you can do it. If B1 is tripping and you think it shouldn't be, you can pull K4 out of its socket, which means this contact here will always be open, and then close the battery input breaker. And if it stays closed, then you know it's either something wrong with K4, or you know it's something wrong with the signal coming out of the board that energizes K4. And then you'd have to do some troubleshooting. If the voltage is greater than 105 volts and K4 is still energizing, then there could be a software setting or something wrong with the control board there, okay? And the last, I think this is the last thing we talk about on the micro-ferros, is the fuse blown. We do have F2 fuse into the bridge. Now remember, I did say earlier on, an IGBT cannot be protected by a fuse. Okay, what the fuse is there for is if an IGBT does fail, and usually fails catastrophically, then the fuse will blow after the IGBT fails to prevent any circulating high current going in, damaging the transformer or damaging any part of the system. Okay, so we always need to check to see if F2 is blown, because if remember we said between here and here we should have greater than 105 volts DC, which means we have to have at the center tap of the transformer greater than 105 volts DC. And if the fuse is blown and we're not getting DC down to this point here, then the inverter will never ever start. So how do you check a fuse? A lot of people get confused about this sometimes, okay? Now, remember, we have DC going in. So the easiest way, if you still have the system energized, the easiest way is with a fluke on volts DC, okay, to go on that side of fuse with your red lead and go on that side of the fuse with your black lead. And if you have 135 volts measured across that fuse, then that fuse is, I hear you all shouting, bad. Okay, if this was a short circuit, if you have 135 on one side of the fuse, you have to have 135 volts on the other side of the fuse. So therefore, there should be no voltage potential across that fuse whatsoever. But if you want to be safe and you want to turn off the charger, turn off the battery, then you can go in with your fluke on resistance, and you can measure between that point there and that point there. And if you measure round about 0 ohms, the fuse is good. Okay. And if you measure OL on your fluke, then the fuse is bad. Okay. So if the fuse is gone, the last thing that we need to check is the IGBTs. And there's a very, very quick way to check the IGBTs. So here's our IGBTs here and here. Okay. What you do is you get your fluke and you power down the system. So we want to turn the charger off, and we want to open B1. And then we get our fluke on resistance, and we measure, we'll put our red lead on this point here, which is the center point of this transformer. It's very important to notice that. The easiest way to get it is on this side of the fuse, and you would have to get the wire number to know which side of the fuse it is. And then we put our other black lead on this terminal here, which is 3N, which is a power connection on the bottom of the IGBTs. If you follow the drawing, you know, these should be open because there's no power going to the system whatsoever. So if you follow this down, you go through the resistance of the transformer, which should be very low indeed. If you know anything, you should know that a transformer has very, very low impedance. So it's as if it's a short circuit. And if this is open, then when you measure these 2 points, you should see OL, or it's at least a very high resistance on your fluke. Okay. And by doing this, by checking at this point here and at this point here, you're actually checking both sets of IGBTs, because if you do get 0 ohms, okay, then that must mean there is a short either that way to that point there, or a short that way to that point there. So all you're doing, if you do find that your fluke anywhere from 0 to 4 ohms really, then there is an IGBT that has shorted. And then what you need to do then is disconnect the power cables from the IGBT itself inside the system, and then test them again to find out, is it this one or is it this one? Okay. In truth, whenever we have an IGBT fail inside an inverter bridge, we always recommend you replace all the IGBTs for 2 reasons. First of all, if one IGBT has failed, then the other IGBT saw high current going through it as well. So we could have significantly weakened it. And the other thing is, IGBTs are made in batches, and we always recommend that the same batch of IGBTs are installed inside the UPS. Okay. I know it's a lot of information. You can go back and watch it on YouTube and pause it and think about it. But that's if the inverter is not running. Now, if the inverter is on bypass, then the control board has some handy LEDs. So you have to open the door and look on the back of the X2 inverter static switch controller. And there are some good LEDs that can tell you something about what has gone on within the system itself. And remember, these LEDs are latching. There is a reset black push button on the X2 control board that will reset these alarms. So first thing you do, if you do see one of these lights on the back, press the reset button after you notate which alarm is on. And if the alarm resets, then that alarm is no longer in. Okay. If the system has transferred to bypass, then the system is always going to transfer to bypass if the inverter fails. So you should always check if you have 105 volts coming in, because if you don't, the inverter is going to shut down because of the B1 input breaker tripping, and it will transfer to bypass. So first thing you should do if it's transferred to bypass is check if you have 105 volts going in. Okay. Now, if the inverter is running, but it has transferred to bypass, there is this little circuit here, and it's called loss of square wave. And basically, what we're trying to do is the secondary of the transformer here is where your sine wave is coming out. And there is some stored energy, surprisingly, in this secondary of the transformer. So if we have a fault in the inverter bridge, you'll actually get about 1.5 cycles of AC out after. Is it 1.5 cycles or 1 cycle? I can't remember. But you will get at least a cycle of power from this tank circuit here and the inductance in the transformer if this side fails. So what we have is we have a loss of square wave circuit that says, okay, if the square wave fails going into this primary side of the transformer, we want to transfer the system to bypass while we still have that stored energy in the transformer. If we waited and we measured the output of this side and waited for it to fail, then we would be transferring to bypass as the system is failing and doesn't have the stored energy. And basically, this goes up to the X2J15 board, and you should have basically a square wave going in there. You can measure it with a scope, but if you measure it just with the fluke, it should be anywhere between 14 to 18 volts AC. If you don't have 14 to 18 volts there, then there's either something wrong with that transformer, which you'd have to get the whole transformer replaced. But usually if you follow this up to X2J15, there could be a break in the wire going all the way up to the control board. And if that's the case, you need to figure out where the wire is broken, or if there's a bad connection at the control board itself. If you have the inverter fail light on, then the inverter fail is measuring the output of the system. So this is not square wave fails, which was this one here. This is actually measuring on the output of the system. So we have a healthy square wave going in, but let's say either there's a short circuit somewhere. It could even be in the transformer or something out on the load. If it pulls down the voltage to below 60 volts AC, then the system will transfer to bypass. So if you had inverter fail on, that is what happened. And then you'll have to try and figure out why the system went down to 60 volts, which can be quite difficult in truth, but at least you know it's not the square wave or it's not the DC if you have the inverter fail light on the board. And then the other thing that would transfer the system to bypass is we have a CT on the output of the system, okay? And basically, this is the CT here, and it has a circuit on it that converts the CT voltage through a burden resistor into a signal. And basically, it's a 10 volt signal for full load. Okay, so if it's a 10 kVA system, full load is usually 83.3 amps, something like that. So if you had 83.3 amps flowing through T202, you would measure 10 volts going to the control board. If it goes above 12 volts, in other words, we go above 120% of the rated load of the system, then the system will transfer to bypass if bypass is available. And the last alarm that I think I'm going to discuss from Micro-ferro system is the crest factor board. It's very difficult to monitor an AC waveform, and if there is any peak currents being seen by the load circuits out here. So we do have a crest factor detection circuit that is looking specifically for peaky load current, because peaky load current, you know, you could measure this with an amp clamp. And remember, I said for a 10 kVA system, it should be 83.3 amps RMS. So if you measured 83.3 amps RMS, you think, well, okay, the system should be okay. But if you put your meter on peak to peak and you saw a huge peak, let's say 300 amps peak load currents, then that's too much for our IGBTs to handle and will probably damage them. So our system will transfer to bypass if it sees high peak current, and that will give you the crest factor alarm on the back of the board. And if F2 fails, then it could be that there was an IGBT failure. Or one thing you could also check is that the ferro-resonant transformer hasn't overheated. It usually will give you indication over a long period of time that the transformer is going to fail. It starts to make a lot more noise than it used to, starts to heat up. So that's why we always perform thermo imaging on all of our transformers during our annual PMs. But what can happen is one of these windings here can short down to ground. And if that happens, then that is going to blow this fuse every single time. Okay, so it's very difficult to tell if that happened. You have to disconnect 16 and 10 and disconnect many portions of the transformer, and then try and just get the main windings and look at them down to ground. And if you have a short, then you do have to replace the transformer. And of course, the last thing, if it's transferred to bypass, is it could be there's something wrong with the inverter static switch control board. And, you know, this is not the time or place to try and say why you would do that or what you would do that. It's just one of those things. If you've checked everything else and none of those things are bad, then it could be that the X2 board has failed. Okay, going to take another drink, then we'll get started on the DPP, which isn't as long. I could go with further depth on the DPP, but I knew I was going to run out of time, and I wanted to concentrate mostly on the ferro resonant on this webinar presentation. So this is the H bridge for, excuse me, a normal inverter. Once again, we've got our positive and negative. When I say normal, it's our DPP, which uses pulse width modulation. And what we'll do is we'll call this Q1, Q2, Q3, and Q4. And the way this works is we turn Q1 and Q4 on, then basically power will go down there. That will make that positive with respect to, if we follow this negative back to here, then that makes that negative. So that would give you a positive pulse on the output with the amplitude of whatever this DC voltage is here, which is usually 135 volts DC. Okay. And then if we turn Q3 and Q2 on, you can see that the voltage will go down to this point here. It will make that side of the transformer positive, and this side will be negative if you follow this down here. And that will give you the negative portion of the output. Now, we're not just switching this at a square wave at 60 hertz in our DPP systems. Okay, there's the power flow one way and the power flow the other. We're actually switching using pulse width modulation. Okay, so what we're doing is we are varying the width of the pulses that we send to the IGBTs. Okay, now look, this is the important thing to remember for pulse width modulation. The amplitude is not changing. So this is 135 volts DC for a normal 60 cell system. Okay, that does not change ever. That's what we're switching if the charger is on and the battery is good. And also, if you measure the frequency of each of these pulses, the frequency, although my drawing is absolutely terrible, the frequency is not changing. Okay, that's still remaining the same, and the frequency used is about 8.5 kilohertz. We are switching at 8,500 times a second. It's crazy, the speed that we switch our IGBTs on in our pulse width modulated system. Okay, the only thing that we are modulating or changing is the width of the pulse. So you can see this pulse here is extremely thin. It's just one line. But if you go into the center of the waveform, you can see that it's much thicker. It's actually that thick. And then we get out to this side here, and it's very, very thin again. So we have adjusted the width of the pulses. And the mathematical average of this pulse width modulated waveform is a sine wave. And basically we just put that through a transformer and capacitors, and it creates a near perfect sine wave on the output. So once again, the red is the positive side of the transformer, and that was Q1 and Q4, and this is Q2 and Q3. Okay, so the square wave pulse width modulated waveform is on the primary of the output transformer, and the sine wave is on the secondary of the transformer, which will have a capacitor circuit in there as well. Okay, and this is what the bridge looks like on one of our drawings. Once again, we have our positive and our negative coming from the battery and the battery charger. Okay, and then you can see we have Q1, Q2, Q3, and Q4. And it is exactly as I said. Let's switch on Q1 and Q4. Power flows down through Q1 down to this point here. That goes down out to the transformer. Okay, and then the bottom side of the transformer gets connected to the negative through this IGBT back here, and that will give us our negative going pulse, because we've got this side is more positive than this side, and the same for the other side of things. So this is just actually what it looks like in our official drawings. And there's the primary of the transformer, there's the secondary of the transformer, and there's that capacitor filter circuit that I mentioned. And as I mentioned before, remember, a fuse is not fast enough to protect the IGBT. So what our control board has in the pulse width modulated system is a circuit that is called IGBT desaturation. It's a very, very big fancy name, and I'm going to try and explain this in the easiest way possible. So when we have our gate drive PCB here, we're not sending a signal to the gate. Okay, that's what the red means. So the collector and the emitter are not connected at this time. We can have positive voltage there with respect to the emitter and negative voltage there, but it's not going to switch because we haven't sent a gate signal. When we do send a gate signal, we have a sensing circuit on the gate drive PCB that is looking at the collector voltage with respect to the emitter voltage. Now, when we turn it on, it should be a direct short. So theoretically, it should be 0 volts between the collector and the emitter, but no IGBT is perfect. Okay, and there is a voltage across that IGBT in normal operation. So we're measuring that voltage and we're comparing it. And basically what we're saying is, if it's less than 9 volts voltage across the collector and the emitter when we're sending a signal to the gate, then that's okay. Everything is good. We will allow the system to keep switching the IGBT on and off. But if we get a situation where it goes above 9 volts, then the gate drive board says, nope, that's not possible. That means that our IGBT has too much current flowing through it. Okay, that's what desaturation means. When an IGBT goes out of its saturation zone. Too much current is flowing through it. It's not in its perfect zone anymore. And the more current that flows through, the higher voltage will be measured across the collector and the emitter. And that means the IGBT could be getting ready to fail at any point. So what we try and do is remove the signal from that IGBT as quickly as we can to prevent the current going through the IGBT and from it destroying itself. And then what will happen is on the gate drive board, there will be an LED that says desat, okay? And here's the gate drive board as part of a drawing on our system. And this is called the top IGBT, and this is called the bottom IGBT, okay? And this is for PCB4. And there is an alarm. There is a desat top and a desat bottom, okay? So basically it's telling you which IGBT the desaturation that's being detected is related to, okay? So what you can do is, if you find that you have desat top, what you can do, because there's always two gate drive boards in any of our systems. There's one there and there's one here that's for the other set of IGBTs. You can swap these two gate drive boards. You can't just swap the cables. You have to physically completely swap both gate drive boards, okay? And it's okay to do that. And if the fault moves with the board, then the board is the issue. If the fault stays with the IGBT, then the IGBT is the issue. I hope that explains that. I'm running out of time, so I am going a bit quicker than I'd like to at the end here. Once again, if the inverter won't start, we have to check that we have 105 volts going into the system, okay? If we don't have 105 volts, it doesn't matter if you switch the inverter on or off. The inverter is not going to start. The software says the voltage must be above 105 volts DC. It measures it at this point here on the control board. If that is not greater than 105 volts DC, this inverter will never start no matter what you do. Just like the B1 auxiliary contact in the Micro-ferro system, we have a switch on the DPP UPS that is called SW2 inverter enable switch. And once again, we're sending 5 volts out on this terminal here. And it's only when we get 5 volts coming back at this terminal here that we will turn the inverter on. So if there's something wrong with this switch and it doesn't allow it to close and allow that circuit to be made, the inverter will never, ever switch on. So if the inverter is not switching on and you have greater than 105 volts DC, the next thing you should check is to make sure that inverter enable switch is closing when you switch it to the on position. And you can either measure at the board itself or on the terminals of the switch itself. You can even switch the system off completely and measure with a fluke on resistance across these terminals. It should be open when the switch is off, and it should be closed when the switch is on. One thing that we talk about when people come to our class in Stafford is in the DPP systems, we have something that's called fast blink, okay? And it's all of our boards have a UCB, which is a universal communication board on it. And we connect our fiber optic cables between each board, and that is how all the data transfer is done within the system. If the signals for these boards did not get sent correctly, you will not get fast blink. And that is the DSP OK light, okay? And it should blink very fast. Unfortunately, I don't have a video to show you, so it's a little bit ambiguous when I say you should get fast blink. But basically, if it's blinking at about once a second or once every half second, then that's slow blink. Something is wrong and the software hasn't loaded correctly. Fast blink is where it's blinking maybe 3 or 4 times a second. And there is quite a difference. If you don't get fast blink, the inverter will never, ever start, no matter what you do. You have to have fast blink because we have checks and balances within the software of the system that make sure that the system has all the right parameters to work correctly. As I mentioned, if we have DSAT top or DSAT bottom, you just swap these two boards around, and if the light was on PCB4, let's say you had DSAT top on PCB4 and you swapped these boards, and the board, you now had DSAT on this side of the system, then you know the board was the problem. If the DSAT stayed in this position, then you know it is this IGBT Q1, and you would have to replace Q1, and we would usually recommend that you replace the gate drive board as well. And to check whether you have a bad IGBT, remember, this is positive, this is negative. There's also a very easy check when the system is completely de-energized. You can clip your fluke on resistance. So clip your red lead to the positive bus, which is wire 10, and then connect your black lead to wire 16. And what you can see is if either of that IGBT or that IGBT fails, let's say Q1 has failed, if you follow it down, that will give you 0 ohms if there was a short on the IGBT. 0 ohms is bad. That means you have a bad IGBT. And this test checks Q1 and Q3, okay? And then you just switch your fluke over to bus 12, keep your other lead on wire 16, and then that, let's say Q2 has failed. That will give you a short circuit between there, and the same with Q4. Okay, so that will tell you either this one or this one has failed, or this one and this one failed, with a very easy resistance check using a fluke. Now, to find out which one has failed, you would actually have to disconnect that wire there and measure across the collector emitter of the IGBT itself. Okay, now remember, you do have to disconnect it because this transformer will give you a back feed. So if this has failed and is short circuit, but this one is still good open, if you went across the collector and the emitter here with this system, with Q1 still in circuit and it being a short circuit, you will read a short, because basically the short will go down here through the transformer and make it look like that one there has shorted as well. So to find out which actual IGBT has failed, you do have to disconnect them from the circuit. Phew! I'm sorry if I went too quick there, guys. Or guys and ladies, should I say. I was trying to get through as much as I possibly can. Okay. So let's see if we've got any questions. Okay, when a loss of square wave happens, is it quick enough to switch to bypass so that power is still interrupted? Absolutely, Eric, that's a great question, and that is why we do have the loss of square wave. In truth, 99.9% of the time, all of our transfers to bypass, due to the inherent nature of the SCRs in the static switch, will happen uninterrupted with less than a cycle of power. The most you will lose is quarter of a cycle, and near enough all load circuits will be able to maintain power during that blip. But yes, in answer to your question, the loss of square wave is designed specifically that it will see the failure. The ferroresonant tank circuit will keep the output of the system going while the transfer to bypass happens, and you will see no blip whatsoever when you see loss of square wave. Okay, let me see if there's any other questions. I don't see any other questions just now. If you do have any other questions, please put them in the Q&A tab. And what I'll do is, while I'm waiting for any questions, I will say our goodbyes. Thank you once again. I know this was a bit more technical than usual, and it did run longer than usual, so if you stayed right until the end, I do appreciate it, because I know your time is precious. You're very busy people, and the fact that you spent an hour with us today is really truly gratifying for us. We hope that you enjoyed it. Somebody has asked, can we provide a copy later? We do not provide copies of our presentations. They are proprietary, but you can share the YouTube links. You can see in the chat that London has put the link to our YouTube channel. This video will be available by the end of the day, and you will also receive a follow-up email with a survey link and a link to the video. And don't forget, the reason why I did this presentation today was because somebody wanted more troubleshooting on inverters, and they filled out our survey form and put, one of the questions is, what would you like us to go over at our next webinar? So please take 2 minutes to complete our survey. London, once again, has put it in the chat bar. Go in there, complete our survey, and tell us what you want us to discuss at our next webinar. We will do everything we can to try and cover that for our next webinar. We are always looking for good ideas. So I don't see any more questions. If you need to contact us, London has put our telephone number in the chat. It's 1-800-635-7300. Just go through the menu tree. You will get to a live person every single time. You can go to our YouTube channel, or you can even contact us via sci.marketing@ametek.com and ask us any questions, and we will get back to you. I really hope this webinar was interesting, that you gleaned some information about how our inverters work, and gave you some things to check if you have an inverter failure, and you can check the IGBTs or the gate signals or something like that. I hope it gave you some more information than you had before you started watching the webinar. Until next time, thank you so much again for watching, and we look forward to hearing your suggestions for our next webinar, and we'll speak to you next month. Thanks very much, everyone.